Hello and welcome to my presentation with the topic investigation on the influence of cold forming and associated residual stresses on the fatigue strength of thin-walled details. My name is Thorben Geers and I'm a scientific assistant at the Institute of Steel Construction at the University of Aachen for 3 years now, and I am pleased that you are interested in the subject area mentioned. To give you an overview over this presentation, I would first like to outline the background of this research project. That is why the project is so important and what possible goals might be. As an introduction to the research results, I would first like to characterize the material used. This includes the choice of sheets under investigation and finally the static and dynamic properties of these materials. A special feature is given here to the test bench because this test bench is relevant for all tested fatigue specimens. I will then explain the profiled specimens, and due to the bending with a defined radius, which becomes relevant in combination with a used material thickness, these show special properties, for example with regard to residual stresses. Finally, I would like to summarize all presented results. But where does the described topic find itself in reality? So actually the construction of high storage racking systems is mainly realized within walled and cold formed steel sheets. This cold forming is realized by so-called roll forming stations or press braking systems. You can see the forming process in the pictures on the right side. The cold forming leads normally to a plastic deformation, which results in a change of material properties in the bending areas, and it definitely leads to residual stresses. Additionally, it can lead to changes of the thickness of the sheets in the bending areas, and it can lead to possible changes in surface conditions. This manufacturing process is regulated by the Eurocode 3 Part 1.3. But these rules do not include design rules for fatigue loads, which increasingly occur due to the automated usage of the racks. Furthermore, the fatigue design rules in Eurocode 3 Part 1.9 exclude thin-walled and cold form members. So as a result, the increasingly automated storage and retrieval of high storage racks, which leads to high fatigue loads, cannot be taken into account in the design via valid standards in Europe. The goal of the described project should be a basis for such standards in Europe. With regard to the virgin material, we tested a lot of different material types and thicknesses, but in this presentation I would only like to present one single type of material because all of the other types and thicknesses don't vary that much in the values of the properties. So in this case, I have chosen the material as 355 MC with a thickness of 3.5 millimeter. The M indicates the thermomechanically rolled material, and the C is the indication for special cold forming properties. We have tested this typically used material for high storage racking systems in the two main directions, so parallel to the manufacturing direction and transversal to this direction. And you can see in the stress strain curves that there is no big difference in the values of the properties. So we have the same Young's modulus in both directions of 205 gigapascal. We have nearly the same ultimate strength of 469 and 467 megapascal, and we have a maximum elongation of 32 or 33%. There is only a small difference in the yield strength, which is 435 megapascal parallel to the manufacturing direction, and we have a lower value of 394 megapascal transversal to this direction. This difference is to be explained by the manufacturing process of the mother coil, but this difference doesn't matter that much. To assess the influence of plastic deformation on fatigue strength, specimens from virgin sheets were compared with specimens from pre-stretched sheets. In order to determine the degree of plastic deformation, points applied to the sheet surface during stretching were documented using two high-resolution cameras. The resulting position of the points before and after stretching then allowed conclusion to be drawn about the stretching. Finally, the results could then be presented in complete strain maps, which you can see on the right side in yellow and red. The strain maps obtained could be used to quantify the strain values of the surface after superimposing them on the sheet surface. Before I present the results of the fatigue strength, I would first like to talk about the specially developed test bench. The monster, that's what we call our test bench, is a resonance test bench. The setup primarily allows for tests in the tensional threshold range only. The advantage, however, is that although the unbalanced exciters in the movable slide in the middle can only generate a maximum force of 6 kN, significantly higher forces with a factor of 5 in this case or more can be generated in the specimen via the resonance effect. The natural frequency or eigenfrequency of the movable slide, which can be controlled via springs, has a decisive influence on the increasing factor. On the right hand side you can see the extension of an experiment and a relatively high scattering of the stress range. This is the disadvantage of resonance. The control does not allow a constant load, which is why a summation of load cycles is necessary with the help of the linear damage accumulation according to Palmgren Minor. However, the high frequency of up to 50 Hz makes it possible to spend comparatively little time on the tests. Anyone who has carried out fatigue tests knows how important the time factor is. The results of the fatigue test with given specimen geometry are now shown here. In this and the following diagram, the SN curve for the highest notch detail 160 according to Eurocode 3 is given for orientation purposes. The results of the fatigue tests are all in the range of the nominal yield stress of 355 MPa. The slope of the SN curve is approximately 25. The orientation of the samples from the mother coil is not relevant. There is no difference between parallel and transversal, which you can see in blue and green. On the right side are the results of the stretch samples. The value of the plastic strain is noted accordingly. However, it can be seen that there is no difference between stretched and unstretched samples. An influence of the pre-strain on the fatigue strength can therefore be excluded. I would now like to move on to the profile test specimens, as they are also used for high storage tracking systems. These specimens are all cold formed and have different geometries. The relationship between the forming radius and the thickness of the material varies. The residual stresses changes accordingly. The evaluation of the test is not done via the induced force, but via strain gauges, which are placed near the point of failure of the inner radii with highest eccentricity, as you can see in the picture on the right side. First of all, I would like to discuss the influence of the ratio between radius and thickness. A series of samples with the same global geometry but different radii and thicknesses was examined. This leads to the same load, but the increased stresses in the notches show different strength on a cyclic load. Specimens with a high R2T value, here the dark shown points, show a strength of up to 320 Newton per square millimeter for 2 million load cycles. The samples with a low value are at 210 Newton per square millimeter. It can therefore be seen that the fatigue strength increases significantly with increasing R2T ratio. The influence of the notch can of course be shown with help of FE models. This is shown here as an example for a single test series. For the stress determination at the location of the strain gauge, the SN curve shown here results. With 2 million load cycles, this gives an average fatigue strength of 104 Newton per square millimeter with a slope of about 5. If the increased stress in the notch base is now taken as a basis, this results in an increase of over 207%. The fatigue strength is then 250 Newton per square millimeter. But bear in mind that the fatigue strength of the virgin and the pre-stretched specimens is significantly higher in the yield strength range. This at least shows that there are other factors which influences the fatigue strength. For example, residual stresses or surface conditions. The investigations have not yet been fully carried out. However, a large number of fatigue tests has been carried out up to date. An assessment of the influence of residual stresses is still pending, but according to the nominal stress concept, high fatigue strength results overall. All results were above a value of 90 Newton per square millimeter at 2 million load cycles. As you can see, most of the values are clearly above this limit. For all individual test series, the slope of the SN curves ranged between 5 to 8. Finally, a summary of the results shown. First of all, the tested material meets all static requirements. The fatigue strength of the virgin and pre-stretched material showed high values in the range of the nominal yield point. The slope of the SN curves is about 25. A difference between the two main orientations and between virgin and pre-stretched material could not be determined. An influence of the cold forming on the fatigue strength can thus be excluded. The curved test specimens also show a clear relationship between the level of the alternating load and the occurrence of failure. The slope of all SN curves is between 5 and 8. It could be shown that the R/T ratio has a decisive influence on the fatigue strength. The quantitative influence of the residual stresses on the fatigue strength still has to be assessed. I hope that you enjoyed the presentation and that I was able to explain the topic in an understandable way. If you have any questions to this topic, please feel free to contact me under the given contact details. Furthermore, I wish you much success for the Eurosteel. Best regards from Aachen. Ciao.